Dan, thank you very much for joining the podcast.
Pleasure to be here.
There are some exciting studies that you performed. You observed light from behind a black hole. Is that accurate?
Yes, that's right. It was really exciting when we first figured out what we were looking at in our observations.
And what's significance of this for people who don't understand what's going on?
And so we can sort of imagine what we're looking at here as black holes, sort of this dense, massive object in the center of a galaxy that is so dense that the force of gravity around it is so strong that nothing, not even light, can escape it. So any light that travels into the black hole shouldn't be able to come out again. Now, what we were looking at is a supermassive black hole in the center of a galaxy that is swallowing gas at quite a high rate. And when this gas falls into the black hole, it releases an enormous amount of energy. And this powers a really bright light source. And we've been trying to figure out exactly how this works, exactly what happens to this gas in its final moments as it falls into the black hole that lets it power some of the brightest lights we see in the universe. And as we were looking at this black hole, all of a sudden, it started to get much brighter, releasing what we call flares. So you can imagine the brightness of the X-ray light, X-rays being a high energy form of light, was pretty constant. And then all of a sudden, it started flaring, emitting these really bright flashes of X-rays. And this is really exciting for us. When we see these bright flashes of X-rays, we can then look for how they echo off of that gas that's falling into the black hole. This light flashes, and then some of those X-rays shine onto the gas that's falling in, and this gives us a pretty special view of this gas falling into the black hole. Right. So we were looking for these echoes and these reflections, and we realized that as the flashes of light, the flares were fading away, we saw these extra flashes of light. And these, we figured out, were those reflections or those echoes from a bit of gas that's actually, as far as we see it from Earth, hidden on the other side of the black hole to us. And this is what's really interesting here. If we're seeing this reflection or this echo from a bit of gas that should be behind the black hole, we shouldn't be able to see it because any light that tries to go through the black hole is just going to get lost. But what's happening here is the black hole is bending the space around it so that this light that comes out of the gas behind the black hole doesn't have to go through the black hole. It actually is able to travel around the black hole, which is why we can see it.
Interesting. And is it based on some theory that you originally came up with and then tried to prove it? Or this is something, some one-off observation that nobody ever thought of discovering?
So the idea of light being bent around massive objects actually goes all the way back to the early 20th century. If not before, actually, there were earlier ideas, but this really became a formal theory with Einstein's theory of general relativity. Einstein was trying to figure out an accurate theory of gravity. And he predicted as part of general relativity that whenever you have any massive object, whether it's a planet, a star, or at the really extreme case that we were looking at, a black hole, that any light traveling close to that object shouldn't travel in a straight line. It should be bent ever so slightly around it. So anything that's massive should act like a lens. And actually, Einstein himself first observed this phenomenon with the British astronomer Arthur Eddington back in 1919. Einstein had predicted that light should be bent around the sun. So during a solar eclipse, when the moon was in front of the sun, they were able to look for the stars that are around the sun. And just as Einstein had predicted, the positions of those stars around the sun were in ever so slightly the wrong place when the sun was in front of them, because the light was getting bent ever so slightly around the outside of the sun just because of the sun's mass. And more recently, this has been seen on bigger scales. We can see that light can be bent around whole galaxies in a phenomenon called gravitational lensing that's recently provided insight to measuring the universe. But now we've actually been able to see probably the most extreme manifestation of this light bending, light that's emitted just outside a black hole that actually gets bent not a little bit around the outside, but all the way around the outside, testing this theory and confirming it once again, but really on the most extreme scale.
That's insane. For my untrained mind, the idea of light bending, it's kind of surreal, especially if it's bending because of gravity. I don't understand how it's working. Like, when did you become interested in the subject of black holes?
So I've always been interested in understanding how everything around me works, whether it's the world, nature, the universe, or even a piece of technology. And that curiosity led me to studying physics at university. And it was during my undergraduate course in physics at the University of Cambridge that I'd started taking courses in astronomy and in astrophysics. And I discovered a really fascinating object. This was a galaxy called Cygnus A. And what's special about Cygnus A is that if you look at this galaxy in the visible light that our eyes can see, it looks fairly unremarkable. It's a little bit bigger than most galaxies, and there's a little bit more going on around it, but there's not a lot that would stand out. But if instead of looking at this galaxy in visible light, we look at the radio waves that are coming from it, we see that something in the middle of this galaxy is shooting out these enormous jets. This is material traveling at almost the speed of light that travels a huge distance outside of this galaxy, slams into the environment around the galaxy, and inflates these beautiful bubbles that we can see on the sky. And these jets are being launched by the supermassive black hole that is in the middle of this galaxy. And I just thought to myself that that is absolutely amazing. I have to understand how that works, how that black hole in the middle of that galaxy is shooting these jets and creating these beautiful patterns on the sky. So that led me into further studies. I stayed at Cambridge to do my PhD, and that's when I really got into my own black hole research, figuring out exactly what's happening as gas falls into the black hole, to learn about all these ways that energy can be released and light can come out and jets can be launched. And that's really what led me to the work I'm doing today.
That black hole thing, this subject is very interesting, and maybe you could tell a little bit about what this actually is. You mentioned that it's something very condensed, very high mass object in the center of the universe, usually, right? Tell me more, like, what does it even mean? Like, how big is that?
Yeah, sure. So when we talk about black holes in astrophysics, what we mean, it's an object that has collapsed under its own weight. So the force of gravity that's trying to pull every part of that object together causes it to collapse under its own weight. And it gets crushed together. And as it gets crushed, as its mass gets pushed into a smaller and smaller volume, the gravity that's causing it to collapse gets stronger and stronger and stronger. And eventually that becomes what we know as a black hole, when the force of gravity becomes so strong that nothing can escape from it, not even light.
And if we're talking about the size, actual physical size, not the mass, how big are they? Is it like a moon? Is it like a soccer ball? Or what is it?
So it depends what the object was that forms that black hole. And so we actually find black holes scattered all through our galaxy. One way of forming a black hole is when a massive star, a star that's tens of times more massive than our sun, comes to the end of its life. And when that star will do a number of things, it'll explode, perhaps in a supernova explosion, and then what's left will collapse down to form a black hole. And when a star becomes a black hole, we're talking about something that's a couple of times the mass of our sun, but compressed into a region of space that's maybe about 10 miles across. So it's something as massive as the sun, but in the size of about a city here on Earth. But then the ones we're looking at in the centers of galaxies are much, much bigger. So there's these stellar mass black holes that form when stars come to the end of their lives all through a galaxy. But we actually think that pretty much every major galaxy in our universe also has a supermassive black hole at its center. And those supermassive black holes in the middle of our galaxies, instead of being tens of miles across and a few times the mass of the sun, these are black holes that are millions to billions of times the mass of our sun, and sort of millions of miles across as well.
When was a black hole first discovered? And do you know from the history the circumstances of that discovery?
Yeah, so there are a couple of different threads that led to the discovery of, if you like, real black holes in our universe. So this idea of a black hole can actually be traced back to the late 18th century. There were ideas of objects so massive that gravity stops the light escaping. And then it was Einstein that really formalized the theory that predicts black holes with general relativity in 1916. But the first object that was actually confirmed to be a real black hole, if you like, actually one that we can see in our own universe, was first discovered in 1964. And this was with the advent of X-ray astronomy. So moving from looking at visible light coming from space to looking at high energy X-ray light. And so through the 1960s, scientists, in particular led by Riccardo Giacconi, were launching X-ray detectors on rockets at first. And then later, NASA started putting X-ray detectors on satellites in orbit around the Earth. And this gave us the capability to look for high energy X-rays coming from space. And this first black hole was one of those early discoveries. What we found was that the X-rays often come from these bright point-like sources, so almost like stars, single points of light, but not shining in visible light, shining in X-ray light. And then when these were first discovered, there were quite detailed studies done on them, looking at them in different respects, trying to figure out exactly what these bright sources of X-rays were. And it was discovered from the way this first X-ray star, if you like, called Cygnus X1, interacted with a companion star that was nearby, that this needs to be something that's about 10 times the mass of the sun and about 10 miles across. And once you start putting that evidence together, once you discover that there's something so massive compressed into such a small volume of space, and also looking at just how much energy is being released in the form of the X-rays coming from it, our theories tell us that this really can only be a black hole, as was predicted by Einstein's theory of gravity.
That's insane. I don't know, man. That's just crazy. How you can predict this kind of stuff? Like, maybe that's why I'm not a theoretical physicist. So, let's imagine that we travel to that black hole. I'm assuming that's not really possible, but let's just assume that we somehow found a way. As we get into the center of the black hole, what are we gonna experience?
So actually there's this common misconception that as you enter the black hole, that something weird will happen to you. Suddenly your perception of the universe will change as you pass into the black hole. I mean, what we mean by going into the black hole, there's different ways to think about that, but the most common way is crossing this place called the event horizon. The event horizon we can think of as being the point of no return. That is where you're so close to this collapsed object that the gravity's gotten so strong that you can't escape. If you're outside the event horizon, you're free to fly around the black hole and escape from it. But as soon as you go in through that event horizon, the gravity becomes so strong that the only way you can possibly travel is straight down towards the center of it. But when you cross that event horizon, your perception of the universe doesn't change all of a sudden. If you're flying in towards the black hole, what you'll see is in front of you, the black hole should look dark because no light can come out of it. But then if you turn around and look behind you, you'll see the light from all the stars in the sky. But as you cross that event horizon, the only way you've got to go is down. And the only way everything around you has got to go is down as well. So if you look down at your feet, you'll still see blackness. No light can come back up from inside. But if you turn around behind you, you'll still see all the stars because all of the light that's come from those stars is just falling into the black hole behind you. So there's nothing particularly special that happens as you cross that point of no return. But what gets really interesting is once you get down to the very center of the black hole. So this is what scientists often refer to as the singularity, is sort of the buzzword for that. And the singularity is, you can kind of think of it as where all of the stuff that's fallen into the black hole ends up. Everything that goes into the black hole is getting pulled down and it's getting crushed together. But it's got crushed together so much that it's become really small and the gravity has become really strong. And this means that Einstein's theory of gravity, general relativity, actually starts to break down. It doesn't work when we start looking at things that are really small. We need to invoke another area of physics called quantum mechanics to tell us how really small scales behave. And actually, it turns out that general relativity and quantum mechanics are really difficult to join together into a single theory. And this is one of the major areas of research in theoretical physics at the moment, how to join quantum mechanics and gravity together to understand what's happening in the black hole. So we actually don't have a really clear understanding of what's down there at the singularity at the moment. And there's lots of ideas that the quantum mechanics tells us that the universe, instead of being static, is in this constant state of flux, and even space and time themselves are in this constant state of flux, rearranging themselves and mixing themselves up all the time. And that gives rise to that there's maybe space becomes more like a foam once you get right down into the center. And there's also some more exotic theories as well that a black hole in our universe maybe even leads to another universe or a distant part of our universe. Now, it's probably quite difficult for us to, the laws of physics as we understand them haven't yet shown us a way that we'd actually be able to travel through this. But yeah, it'd be really interesting to actually be able to see what's going on at the center of the black hole. But unfortunately, that event horizon is protecting what's in the black hole from being discovered. No light and no information about what's going on down there can get out. So it turns out it's actually really difficult to test theories of the center of a black hole.
Is it difficult or it's actually impossible from our understanding of physics?
So it's impossible from our understanding of physics to directly observe what's going on inside the black hole. As far as we understand the laws of physics, no light and no information should be able to travel back out through the black hole. But there might be other ways we can test the theory. That theory that predicts something that goes on inside the black hole might also predict something we can observe outside the black hole. And that might give us a handle of what's going on inside.
Is there a way for humans to create a black hole in a lab?
So this has been something that's been discussed a few times. And actually, this was one of the concerns that ended up, sort of a concern in sort of popular science and media circles when they turned on the Large Hadron Collider at CERN, the big particle accelerator, where they're taking protons at extremely high energies and crashing them into each other to explore the high energy limits of particle physics and theoretical physics. And so to form a black hole, theoretically, all you need to do is take something and crush it down so that it's within a critical radius. And that radius depends on the mass. So you could turn the Earth into a black hole if you could crush it down to be about 1/2 inch across. And when you've got these protons being fired into each other in a particle accelerator, they could potentially get close enough to each other that they are within this critical radius, that they could form a really, really tiny black hole that's the size of subatomic particles. But I mean, this often stirs up these sort of horror stories of scientists make this tiny little black hole in the lab and it pulls in everything around it and destroys the Earth. But luckily for us, that never actually happens. Turns out that, well, humans didn't invent the particle accelerator. Nature did it first. There are these things called cosmic rays, these high energy particles that get launched all across the universe. And when these cosmic rays hit the top of the Earth's atmosphere, if you can make a black hole in CERN, you could make a black hole in the upper atmosphere as well. But it was actually a theory of Stephen Hawking's that saves us from that. One of Stephen Hawking's great discoveries is that a black hole will slowly evaporate. Now, a black hole that we look at in the center of a galaxy or when a star dies is so big that it will take longer than the age of the universe to evaporate. So we never notice this. But these tiny little black holes, if they did get formed in the Large Hadron Collider or in the upper atmosphere, they're so small that even before we'd notice they were there, they'll already have evaporated.
Got it. So if they evaporated, everything that got to that singularity also evaporates, right?
Yes. So the idea is in this theory is that the evaporation of the black hole is due to light and other particles that are created at the event horizon. So it's sort of the black hole kind of evaporates into low energy light and other emission that comes out into our universe.
Got it. Yeah, I just thought like if in physics, if some things just don't disappear like that, right? It's yeah. It's so that's what another mystery is probably how that works, right?
Yeah, exactly right. So yes, the black hole can't just disappear. What's in it just gets converted into light in our universe. Is the theory. It's not something we've been able to detect yet, but it's a pretty solid theory.
Well, some things that I've read is distortion of time around a black hole and in space in general. Can you speak of that? Because it's another concept that I just can't comprehend.
Yeah, so one of the important things about general relativity is that space and time are part of the same thing. So we're used to being able to travel around in space. We can walk forwards and backwards, we can go left and right, and we can go up and down. And time is just another direction that adds to the 3 dimensions of space that we're used to. Now, the difference between time and the other dimensions is that we're not able to control the way that we travel through it. We have to travel forwards in time. But Einstein's theory, general relativity, says that gravity is the manifestation of space itself being bent around massive objects. So when you have a planet like the Earth or a star like the Sun, or at the extreme end, the black hole, the mass of that object is bending the space around it. And the bending of the space we live in is what we perceive as being the force of gravity. The reason we fall towards Earth if we jump up is that space underneath us is curved. So as we follow the curve of space, that's what brings us back down to Earth. And because time is just another one of those dimensions, time gets warped in exactly the same way as space. I mean, this is something we can actually measure and we can observe. And what this means in practice is the closer you get to a massive object, whether it's the planet Earth or the Sun or the black hole, time actually runs more slowly for you. So if we're both out in space and we both have a clock, and we know our clocks are synchronized, and we send a message to each other every time the second hand ticks on those clocks. If I'm sending you those messages, you'll receive a message from me every second. But if I start falling towards a black hole, the closer I get to the black hole, you'll start measuring a longer and longer time between the messages I send. I'll still think I'm sending you one message a second, but you'll be receiving them maybe once every 2 seconds or once every 3 seconds as I get closer to the black hole. And this is something that is not only something that we've tested experimentally, but it's actually become really important in our day-to-day lives. Because GPS satellites are based on clocks. And the clocks on the GPS satellites are much higher above the Earth than we are. So the gravity they experience is much weaker. So the clocks on those satellites actually tick faster because they're further from the planet Earth. So for GPS to work, we have to understand exactly how the Earth's gravity is slowing down the time up there, and also how the motion of the satellite affects the passage of time as well. So not only have we tested this, but if we didn't understand this, our GPS system just wouldn't work.
You know, you explained it very well, but I still don't understand how it's possible. But I got
Yeah,
that. I got the idea. So
it blows your mind.
I know, yeah. Like, have you seen Interstellar?
I have, yes.
So they show that concept quite well there, right? Like when they travel close to a black hole, he returns and suddenly they're like 50 years or something past, even though they were out for a couple of hours.
Yeah, exactly right.
Is that extreme? Can that get that extreme?
Yes, it can do, actually. So around a black hole, the warping of space and time is really extreme. And actually, once you get to that point of no return, the event horizon, your time as compared to somebody a long way away actually stops entirely. If you get all the way to the event horizon of a black hole and someone's looking at you from the outside, as far as they're concerned, your time will have completely frozen. So if we go back to that sort of experiment we set up before, where I'm falling into the black hole and you're receiving my messages, the time will get longer and longer and longer. But by the time I've crossed the event horizon, you'll completely stop receiving my messages. The time between them will just get so long. So it won't be that I suddenly disappear when I cross the event horizon. It'll be that the messages just get further and further apart until there's just an infinite time between them.
Obviously, biological species can't be that close to a black hole. They probably get crushed or something. But if they were, does it mean they can live forever? Or it has very different, biological clock is very different from that type of clock?
So the biological clock in this context isn't anything special, but there's something kind of weird here that actually is almost impossible to get your head around. But the theory actually says that there's, so this is the type of thing that, so because we can't really visualize this, it's something that we sort of have to let the mathematics do the talking for us and explain it for us. And what the mathematics says is that there's no such thing as absolute time in our universe. This was, so Einstein's theory of gravity is called general relativity. And it's that word relativity essentially means that everything in our universe is relative. And no one person is more, their view of the universe isn't any more correct than anybody else's. And this means there's no such thing as an absolute time. So when I've gone very close to the black hole, as far as you're concerned, my clock will have slowed down. So you'll see my aging process being very slow, like the messages that I send to you get further and further apart. But as far as I'm concerned, my clock is just ticking as normal. Mm-hmm. And so as far as I'm concerned, a second will still be a second, a year will still be a year, and I'll still have a normal lifespan that will be some number of years as far as I'm concerned. It'll just be those years are different to somebody else's years. And this is kind of actually sort of one of the fun sort of toy problems that are often given to physics students. It's something called the twin paradox. And you have two twins on Earth who are the same age. And one of those twins goes on a long distance space flight and comes back again. And it's not just being close to massive objects that slows your time down, but traveling fast also causes your time to slow down. And essentially what happens in this sort of thought experiment is that the twin that's gone traveling, because their clock is traveling slower than the one that stayed behind, actually comes back and they're younger than the twin that stayed on Earth.
That's bizarre. You mentioned that even traveling faster also slows the time.
Yeah.
How fast are we talking about?
So to really notice this effect, you need to be traveling pretty close to the speed of light. So we're talking the effect, maybe if you've got a really accurate experiment, comes in at sort of maybe 80 to 90% the speed of light. But actually the experiments that have been done that actually confirm that this slowing of time really happens, we're actually looking at subatomic particles that travel at 99.9 something percent the speed of light here. And this is something we can observe. There are these subatomic particles called muons that are created by cosmic rays when they hit the top of the Earth's atmosphere. And these muons have extremely short lifetimes. So there's no way they should be able to reach the Earth. We shouldn't be able to see any muons on the Earth that are created in the upper atmosphere, but we do. And the reason that we do is that they travel so fast that their time has slowed down. So while we don't think they should be able to survive, in their perspective, time is traveling much more slowly. So they've got plenty of time to travel to the Earth.
Interesting. And how, just approximately, how much difference that there is in time within our galaxy, within solar system? It's probably just milliseconds. It's not like that are years apart, right?
Yeah, it's pretty small. It's of order milliseconds, depending on sort of where you are in the galaxy. And I mean, it all depends on how fast you're traveling and how close you get to the stars or the black holes.
Gotcha. So you obviously spend a lot of time looking at the sky, literally, right? Like if you had a chance to actually travel to one of those places in the universe, where would you go?
So that's a hard question to answer. And I think actually I'd like to cheat on that a little bit. So I said that space and time are essentially the same thing. So if I can travel to a time in the universe instead of a space, and that time would probably be about 10 billion years ago. And we can actually look back in time 10 billion years, because if we look at really distant galaxies, the light that's traveling to us from those distant galaxies has so far to travel that we're actually not looking at those galaxies as they are now. We're looking at them as they were when the light left. So if we're looking at a galaxy that's 10 billion light years away, the light's taken 10 billion years to get here. So that means we're seeing them not as we are now, but as they were 10 billion years ago. And that was a really interesting time in the history of our universe. Looking at those galaxies that are 10 billion light years away, what we find is that the black holes were much more active then, and the galaxies were still growing then. A lot of stars were still being made in our universe then. So by looking at this particular slice of history in our universe, we can actually learn a lot about how black holes feed on gas and the role those black holes were playing in helping the galaxies around them form, and really see the galaxies come into the forms that we see them today.
So why did they stop being that active?
And so we actually think that every galaxy in our universe that has a supermassive black hole in its center goes through this active phase at some point in its life. And this galaxy we were looking at, that we saw the X-ray echoes in, is one that's pretty nearby. So we were able to see it as it is pretty much today in the not too distant past. But we actually think that every galaxy has its black hole that's feeding on gas and powering this really bright light source in the center of it at some point in its history. And for some reason, that light source shut off. We don't fully understand why, but we think it's got something to do with eventually it just runs out of gas around it. So it's not so the black hole can only really feed on the gas that's very close to it. Anything that's further away is just too far for the black hole to fall into. So eventually they probably ran out of fuel and they just sort of shut off, like the black hole in the center of our own galaxy. It still feeds occasionally and lets off little flashes of light, but it doesn't have this huge amount of gas falling into it.
I'm curious if you're a fan of sci-fi movies, given your expertise, or conversely, you watch them, you're like, oh, this is not possible. This is nonsense. I'm not gonna watch it. What's your take on sci-fi?
I enjoy sci-fi a lot, actually. I really enjoy the premise of a lot of sci-fi movies and how we can take some of the laws of science as we understand them, but then really get creative with them and start asking, what if it was possible to fly across the galaxy? And what if it was possible to visit these other planets and meet alien races? There's a huge amount of fun in the genre. And critiquing the science, I think, is a part of the fun of watching it.
What's the most realistic one, in your opinion?
I think actually Interstellar probably wins the prize for being the most realistic sci-fi movie. But that's not by accident. So Professor Kip Thorne, who is one of the most well-known and respected black hole astrophysicists, was the science advisor on Interstellar. So they deliberately crafted a lot of that movie around the sort of amazing theory of black holes as we understand it. So a lot of the images they created of the light bending around the black hole and how time slows down when you get close to the black hole, all of that was completely realistic and drawn from the theory. And then they were a little creative as well. They sort of ran with some of our theories and said, okay, what if it was possible to extend that theory a little bit? So they came up with they had a wormhole that they were able to travel through to take a shortcut to the galaxy. And that's kind of rooted in the theory of black holes. But as far as we understand it, it's not possible to keep a wormhole open long enough for us to travel through it. So there was a little bit of a creative license on the theory there. And then they got completely creative with the theory of what happens when you fall inside the black hole, which I think is forgivable.
Wait, let's talk about the wormhole for a second. It sounds insane to me. Like, can you explain that again? Like, so you can actually use this wormhole to go from one galaxy to another? To shorten the time?
So that's the idea. So we can think about the universe, the space, as being kind of like a sheet.
Yeah.
And then the black hole, the massive object that collapsed to form the black hole, creates a dent on that sheet. So this is only a two-dimensional universe. It's a flat sheet that we've made a dent in. And the black hole is the dent in that sheet. But that dent in the sheet, you could kind of imagine extending that dent into a tunnel, particularly if the universe, the sheet, wasn't flat, but it sort of curved round on itself. You could imagine that this dent we've created is a tunnel on this side and it connects to another tunnel on the other side. But
wouldn't you hit the singularity on your way?
Yeah, so there's all of these things. So you could potentially hit the singularity, but we actually get into the realms of quantum mechanics there. So there might be a way through the center. But actually, there's a bigger barrier. It's not just the singularity that stops you, unfortunately. The laws of physics has other ways of stopping us taking these shortcuts across the universe. So if you remember, I said that time was part of space.
Yeah.
It's not just the time that bends. It's not just the space that bends around the black hole, it's the time as well. And unfortunately, if you create a black hole, a wormhole, sorry, a tunnel by bending space into this tunnel, the time also plays a role in that. So that means your wormhole that you've made has a ticking clock associated with it. And if you run through the theory fully, it turns out that if you could create a wormhole, it would appear, the tunnel would appear through to this other, either the distant part of our universe or to another universe. But then as soon as the tunnel opened up, it would pinch off again and close. And if you were traveling at the speed of light, and nothing is allowed to travel faster than the speed of light, but if you were traveling at the speed of light, you would reach the singularity. You would hit the center right at the moment it pinched shut.
Holy shit. That's
but unfortunately for us, we have to travel more slowly, so we'd never be able to keep up with it. But there are some ideas about keeping it open, but...
Gotcha. And how do you come back? You need to keep it open?
If you wanted to take the shortcut back, yeah, you'd either need to keep it open or you'd need another wormhole that took you the same direction.
I don't even know how to continue this. This is insane. It's blown my mind. So is your life this exciting, or it full of boring stuff day to day?
I think it's a little bit of both. So when you're doing research, it often runs in sort of fits and starts. So a lot of time we spend sort of convincing our peers, the community, that it's worth doing the experiment. So to do the observations and the experiments we want, we need to be able to use the space telescopes that are able to detect the X-rays coming from black holes. And there's a lot of scientists that want to be able to use those telescopes. There's only a few of them, and there's a lot of scientists that want to look at specific things. So the first thing we have to do before we can really do anything with these observations, we have to get the observations. And to do that, we have to write proposals explaining why we think what we want to look at is interesting and why this is going to be groundbreaking science. So a lot of time, I'd say, we spend writing these proposals, and they're not always successful. So then you have the frustration of, oh, we weren't successful, so we're not going to be able to do this. And then eventually you are successful and you get the time on the telescope. And then you sort of get this really exciting moment when the data from this space telescope is downloaded to you. So it gets downloaded from the satellite into a big computer center on Earth, and then it gets sent to you, and then you get to be the first ever person that's looked at either this particular black hole or at least these particular observations of the black hole, and then you sort of look. And then we saw these really exciting bright flares, these bright flashes of X-rays going off. And it's pretty amazing when you see that. And then when you spend a while sort of really digging into those observations, checking your theories, really working hard on the data to make sure that first of all, that all the data are accurate. You do lots of tests on it to make sure that nothing went awry with it. And then you start thinking about the theories that can explain your data. And then we need to figure out what other theories can explain the data. Are we really looking at what we think we're looking at, or is there something else that's going on that's fooling us here? So that can be quite a long, quite a slow process. And then eventually sort of the understanding comes out. And then you realize, wow, yes, we really are looking at these echoes of light from the far side of a black hole. And that's a pretty amazing feeling when you do that. In particular, there's one really neat thing I like to tell my students, that no matter how small a discovery you think you've made, or no matter how small a thing you're looking at in either your theory or your observations that you've got, there's a brief moment when between you finishing this work and you going to tell one of your colleagues about it, when you are the only person in the world that knows what you've just discovered.
Wow, that's fascinating. So what do you think, how significant was your discovery of your observation of that light?
So I think there are two aspects to this. And so on one side, we're sort of confirming this prediction of general relativity. And now this is a prediction that's been confirmed before. I mean, as I said before, I mean, we've seen the bending of light around the sun. Einstein saw that himself in 1919. We've seen the bending of light around massive galaxies, and the Event Horizon Telescope saw evidence of bending of light around black holes. But we were really pushing that theory to its most extreme limit, saying, yes, this theory still behaves as it should when we're looking really at the extreme bending of light from all the way around the black hole. So we're saying we can really stretch this theory to its extreme and it still holds true. But the other side of this result is what we'd be able to do with this sort of capability. So we're looking at how these bright flashes of X-rays echo off of the gas that's falling into a black hole. And by doing that, we're understanding how we can actually create a map of that black hole. So the Event Horizon Telescope produced those amazing images of the black hole in M87, where we actually saw the shadow of the black hole and the ring of hot gas around it. But there's only a couple of black holes that are big enough and close enough to Earth that we can actually get that image. But by looking at these X-ray echoes, we're learning how we can actually reconstruct that sort of image or that sort of map of this extreme environment just outside a black hole. And this is a technique we're going to be able to use to find out what's happening outside black holes all across our universe, to understand all the different processes that are happening, and with the end goal of really understanding what happens to gas as it falls into a black hole and how that gas is powering some of the brightest sources of light we see in the whole universe.
That's fascinating. So what would be the next step for you? You're still digesting the data, I'm guessing, right now. You're still excited. Is there already something branching out? You're thinking, oh, what about I test this or that on that? Or you still try in the position of trying to understand what exactly which direction you're going to go?
So there's a few different things we're doing at the moment. So the next immediate thing is, these X-ray echoes were just the first discovery we made from these observations. And the great thing about looking at these black holes that are emitting X-ray flares is there's so much going on. There's so much to learn about there. So we're still looking at those data, looking at other aspects of the X-rays and their echoes to learn about the actual source of that high energy X-ray light. That's one of our big goals, to really understand how those X-rays are produced, how the black hole is powering such a bright light source. So that's part of our studies. We're also extending these studies to many other black holes. We're observing new black holes with our X-ray telescopes all the time. And we're just starting to think about and design and develop the next generation of X-ray space telescopes at the moment. And that's another project that I'm incredibly fortunate to be involved in.
Wow, that's fantastic. Oh, you have to promise me, when you win Nobel Prize for this or for some other stuff, I'll be the first person to interview you.
Absolutely.
You're on camera, this is recorded. Ben, thanks very much for being on the podcast. I really appreciate it.
Thank you for having me.